Let us see in this video what is the force experienced by a charged particle in a uniform magnetic field. Now, what is seen is that whenever we have a moving charged particle in a magnetic field, it experiences a force. And the force that it experiences is given by this expression. Force is QV cross B, where V is the velocity of the charged particle and B is the magnetic field. Now you can see from this expression itself that if V is equal to 0, that is, if the charged particle is stationary in the magnetic field, then the force it experiences becomes equal to 0. That is, do remember, a stationary charged particle placed in a magnetic field experiences no force, unlike in the case of an electric field. In case of an electric field, if we have a charged particle, be it moving or stationary, it experiences a force. And we know the magnitude of the force experienced by a charged particle in the electric field is given by F is equal to Q into E. But for now, do understand that only a moving charged particle moving with a certain velocity, of course, experiences a force in a magnetic field. Whereas if it is stationary, it experiences no force. Now we see that the force is given by the cross product of V and B. So therefore, the direction of the force is given by the right-handed screw. As we already know that in case of cross product, the direction of the product vector is given by a right-handed screw. So therefore, if this is the direction of V lying in the xy plane, B along the y-axis, then when we rotate the right-handed screw from V to B, the right-handed screw comes out along the z-axis. So therefore, this will be the direction of the force. So magnitude of force experienced by a moving charged particle in the magnetic field is given by this expression, and the direction of the force is given by the right-handed screw, don't forget. Now let us look at different cases. If theta is 0 degrees, then sine of 0 degrees becomes 0. So therefore, the force experienced by the charged particle becomes equal to 0. Not just that, if theta is 180 degrees, then also sine 180 being 0, so the force experienced by the charged particle in this case also becomes equal to 0. I should have incorporated both of these 2 points together, but do understand clearly that from these 2 points we get to see that if the charged particle is moving parallel to the magnetic field. Parallel meaning in the same direction as B or in the opposite direction to the direction of the magnetic field. Then the force experienced by the charged particle will simply be 0. The next case, if theta is 90 degrees. If theta is 90 degrees, then sine 90 is 1. So therefore, in that case, the charged particle experiences the maximum force, F, which is equal to QVB. And in this case, what happens is we will see the charged particle moves in a circular path. So I've already told you these points. If the charged particle is stationary in the magnetic field, the force it experiences is 0. Whereas in case of an electric field, the charged particle be stationary or mobile, it experiences a force equal to this. So therefore, if we have a combined electric and magnetic field, then the total force the charge experiences is given by F is QE plus QV cross B. This force is also called Lorentz force. Now let us give a look at what the motion of a charged particle moving in a uniform magnetic field will be like. And we discussed the case wherein the velocity of the charged particle is perpendicular to the magnetic field. So the crosses that you see in here are representing the magnetic field. And these crosses are telling us that the magnetic field is perpendicular to the plane of the paper, but going inward. We could also have magnetic field being represented by these dots. Now these dots are also telling us that the magnetic field is perpendicular to the plane of the paper, but coming perpendicularly outward. So wherever you see fields represented by crosses like this, you have to understand that the field is perpendicular to the plane of the paper and going perpendicularly inward. Whereas whenever you see dots representing fields, you have to understand that the field is perpendicular to the plane of the paper but coming perpendicularly outward. The reason being that magnetic field is a vector quantity. and a vector is represented by an arrow. So when the arrow is going perpendicularly inward, it's like you are only seeing the rear end of the arrow. So this is the rear end of the arrow that you're seeing. And whenever the vector is coming out perpendicularly, it's like the arrow is coming out perpendicularly and you're only being able to see the tip of the vector. So these are the tips of the arrow that you are getting to see. So coming back to motion of a charged particle in a magnetic field, in here we have a charged particle moving perpendicular to the magnetic field. Let us say a charged particle enters the magnetic field in this direction. And mind you, the magnetic field is perpendicular to the plane of the paper. So the initial velocity of the charged particle is in this direction. So since the velocity and the magnetic field are perpendicular to each other, so therefore the force experienced by the charged particle will be this much. Now talking about the direction of the force, the direction of the force is given by a right-handed screw. So when we rotate the right-handed screw from the direction of the velocity to the direction of the magnetic field, which is into the plane of the paper, what happens is the right-handed screw, it's like rotating in this direction. So the right-handed screw goes in the inward direction. So therefore the force experienced is in this direction. So this force, it tends to take the charged particle towards the left-hand side. So the charged particle now is moving in this direction. Now again, the velocity is in this direction. The magnetic field is perpendicular to the plane of the paper. Now when you rotate the right-handed screw from the direction of the velocity to the direction of the magnetic field, which is in this direction, what happens is the right-handed screw again goes inward. So the force is experienced in this direction. So this force again tends to take the charged particle in the downward direction. So the charged particle eventually moves in the downward direction with the velocity v. Now again, the velocity and the magnetic field, which is perpendicular to the plane of the paper, in the inward direction. You apply the right-handed screw rule. So when you rotate the right-handed screw from the direction of the velocity to the direction of the magnetic field, what happens is the force experienced is in this direction. So the charged particle eventually starts moving in this direction. So again you apply the right-handed screw rule. You move the right-handed screw from the direction of the velocity to the direction of the magnetic field. The right-handed screw is rotating in this direction, because of which the force therefore will be experienced in this direction. So eventually what happens is the charged particle again starts moving in this direction. And the charged particle will continue to move in a circular path like this. So when the velocity of the charged particle is perpendicular to the magnetic field, what happens is the charged particle starts moving in a circular path. Now do remember in here that since the force is perpendicular to the direction of velocity, so therefore this force will not produce any change in the magnitude of the velocity. It only changes the direction of the velocity or the direction of the charged particle. So the charged particle continues to move in this circular path with the same constant velocity v. So this would be a case of uniform circular motion. Also, since the charged particle is moving in a circular path, obviously centripetal force comes into play, and the centripetal force is provided by this magnetic force itself. Therefore, the magnetic force has to be equal to the centripetal force mv squared by r, where r is the radius of the circular path, and thereby the radius of the circular path comes out to be mv upon qb. And also the time period of rotation t, which is the distance upon speed, the distance that the charged particle travels is the circumference of the circle, 2 pi r. So divided by its speed. So this is equal to 2 pi r upon, from this expression you can see v is q b r upon m. So that is exactly what I've written, and thereby we get the time period is 2 pi m upon qb. You are also sometimes asked to find the expression for the momentum of the charged particle. Now as we know, momentum is mass into velocity, so you can see the momentum is equal to qb into r.